In this video, all we're doing are running through the practice exam for our second unit. And the first problem starts off, find the next item in the pattern. So 2, 3, 5, 7, 11, what's next? 15. The next one should be 13. And we're not asked to identify it, but the object that you should recognize, those are all prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, 23, and the pattern would continue from there. Secondly, make a table of values for the rule x squared minus 16 plus 64 when an integer is 1 to 6. First off, this particular thing is going to take quite a fair amount of work. We would have to create our value, x, and then create a table for x squared minus 16x plus 64 for x equals 1, x equals 2, 3, 4, 5, 6. All of these pieces are right here. Make a table of values from 1 to 6. That's what our directions have told us to do. Recognizing that time is, of course, a valuable asset, we can use our calculator to do all the number crunching for us. For instance, we could go through and put in 1 to the second power minus 16 times 1 plus 64, and I have minus instead of there. 1 squared minus 16 times 1 plus 64, hit enter, and we get 49 for our result. So we could get then 49. Doing the exact same thing, we could go with 2 and say 2 squared minus 16 times 2 plus 64, and we'd get 36. And we could continue putting this in for 3 and 4 and 5, but we are building a table, and I'd like to remind you that this calculator has a table feature. Right up here in the yellow, you'll see it says table. So to access it, we could come in and type in our equation, x squared minus 16 times x plus 64, and then we can go access second and table, and right here we go. Here we go. Plug in 1, you get 49. Plug in 2, you get 36. Plug in 3, you get 25. And so building the table is a feature that's already programmed into our calculators. It's fairly straightforward just to copy them then. 49, 36, 25, 16, 16, 9, and 4. All right, so there's our first part. Continuing with the directions. Make a conjecture about the type of number generated by the rule. What do you think about these numbers? We'll spot a pattern and make a guess. That's what a conjecture would be. So there are different ways that we could do it. Some people could recognize and say 7 squared, 6 squared, 5 squared, 4 squared, 3 squared, 2 squared, and we could continue the pattern down with 1 squared, 0 squared. You could make a conjecture if you recognize this. One of the other pieces that, CJ, you just told me, you spotted the pattern of subtract 7. Sorry, subtract 7. I said that one wrong. It's subtracting 13, subtracting 11, subtracting 9, subtracting 7, subtracting 5. And if we wanted to continue that pattern, we could say subtract 3, subtract 2, subtract 1, subtract zeros. Okay, so we could continue the pattern and simply say, does it continue? What conjecture you make is based on what observations you see. Well, which one did you see first? Did you see the red or did you see the blue? Okay, more people in class said they were spotting the perfect square, so we could make a conjecture based on this observation, and we'll simply say, well, what's your guess? We could say something like the results are going to perfect squares. We could say something like each one is a square of a smaller number. Whatever guess you make, that's going to be up to you. I can't tell you what observation that you'll see. I can't tell you what you were thinking. Now, you could phrase it out this way. Now, although you could put your conjecture down like this, that's not a really, really precise way of describing it. We could be a little bit more precise and say the results are a decreasing list of perfect squares. Because we are recognizing 49, 36, 25, 16, 9, 4. As we continue, the numbers have been getting smaller and smaller and smaller. So we could make the guess that it's based on a decreasing order. What conjecture you make, it will be made up to you. Now, to continue this, we're told, continue your table. Basically, keep going. If we keep going with 7 and 8, what results do we get? Well, it's kind of nice that we still have our calculator, because we can simply scroll down and see what we get with 7 and 8 and 9 and 10 and 11 and so on and so forth. As we continued the table, we would have gotten 1, 0, and then it continued to 1. Which value of x generates a counterexample? 9 does, because we had to guess that it was a decreasing list of perfect squares, and 9 shows us that it actually wasn't. It does not decrease forever. It starts to increase after a while. And so we can simply say x equals 9 is my counterexample. Continuing to number 3. Is this conjecture valid by the law of syllogism? Okay, syllogism tells us. Syllogism was based on if we had P implies Q, and we had Q implies R, these two things merge together to tell us P implies R. In particular, if this part's true and that part's true, stop erasing, come on. The board doesn't like me. Hey. True. Okay. If these two pieces are true, we know the third part will be true as well. Syllogism basically just bridges the gap. So, based on the given, is this conjecture valid? Yes. Well, let's check to see if it fits this structure. If you're in California, then you're in the West Coast. If you're in Los Angeles, then you're in California. So the pieces we had were P implies Q. We had if you're in, why did I write down, oh, we had R implies P. Does this fit the law of syllogism? And you want to be careful because it's not about the letters. When we had this stuff written up on top, we were bridging over the Q. The letters are not important. The fact that something was creating the bridge through the logic, creating that chain, that's what's important here. Is that here? Yeah, because we have R connecting to P, we have P connecting to Q, and this is what builds our bridge, telling us the chain logic will come together for R implies Q, and so this is a valid conjecture based on syllogism. All right, continue. Use syllogism to draw a conclusion. Now this one is not saying, is it valid? We actually have to apply it and come to the end of our chain. If two lines are perpendicular, then they form right angles. If two lines meet at a 90, then they are perpendicular. Okay, so what is the structure that we have? We should also note we have another piece of given. Two lines meet at a 90-degree angle. That's our R. So we are told R is true. We are told that R implies P is true. We are told P implies Q is true. So when we build our chain of logic, we know that these pieces, true will imply true, will imply true. Where is the end of our chain? The end of our chain is the conclusion, the last true thing that we know. So Q is our conclusion. The two lines form right angles. And it's worth noting that the things in the purple are the only stuff that needed to be written down. All the pieces in the red are just thoughts. They're the pieces that you should recognize. They're what should go through your head as you're solving the problem. But they don't have to be written down, because we know that you can follow a chain of logic in your head. Continuing further, write the conditional and the converse for this biconditional. Remember that a conditional statement has what format? Conditional is P implies Q. A converse has what format? That's Q implies P. And the biconditional is P if and only if Q. Just for the sake of completeness, please remember that the inverse is not Q implies not P. Also remember that the contrapositive, I've got that backwards. Contrapositive is not Q implies not P. The inverse, had those switched around there. I don't know what my brain was thinking, but I had them backwards for a second. This problem does not ask us for inverse and contrapositive, but they're all a related topic, so you should be prepared to do any of them. To actually address this, we were asked for the conditional, and we were asked to write up the converse. A rectangle is a square if and only if all four sides of the rectangle have equal length. Essentially, we're finding our P and Q. So our conditional if a rectangle is a square, then wish this thing would stop glitching out with the eraser. All four sides have equal lengths. And admittedly, I'm being lazy right here. I mean, it's not that difficult to write out the words, but I'm trying to save some time. And so I'm writing out a picture of a rectangle instead of writing the word rectangle. I'm writing down the symbol for equal instead of writing the word equal. Ultimately, the piece that we care about is, are you able to effectively communicate your ideas? Can you understand what I'm trying to say?
Yep.
Then we're okay with this methodology. As long as there's no confusion, we're okay with using symbols in math. For the converse, we need to flip it around. If all four sides of a rectangle have an equal length, then the rectangle is a square. A badly drawn and ugly square, but we're not seeking precision in a drawing, we're trying to communicate ideas, so we don't need perfection. Here is a similar problem. For the conditional, which we know is P implies Q, write up the converse, write up the biconditional. Very, very similar, so we'll make sure that we actually get them all included. Well, what is the hypothesis for our statement? If the figure is a right triangle with sides A, B, and C, then A squared plus B squared equals C squared. Recognizing this information, we'll write up our converse, we'll write up the biconditional. So the converse, if Q then P. Okay, we've got the converse.
Wait, so converse
And continuing for the biconditional, remember that the biconditional will use if and only if. We could use the double F to shorten that. So a figure is a right triangle with sides A, B, C, if and only if A squared plus B squared equals C squared. And just out of curiosity, I want to check in with something. You've seen this before in your earlier classes. Do you recognize what famous theorem this is? Yeah, this is the Pythagorean theorem. I wanted to quick point out that the Pythagorean theorem does have a converse where you can use it to say, this is why I know it is a right triangle in the end. And we will address those ideas in a future lesson. Continuing further, write the definition as a biconditional. Well, an object worth noting, an acute angle is an angle whose measure is less than 90 degrees. Whenever you work with a definition, you will always have your vocab word and you will have its actual definition. The vocabulary word and its definition, those should be the front and back, the hypothesis and conclusion for your biconditional. we could write this down then as, and of course there's more than one way to do it. An angle is called acute if and only if its measure is less than 90 degrees. So yes, an 89-degree angle would be called acute. An 89.999 degree angle is still called acute. Now, fortunately, since proofs are still a very new topic, I am not yet asking you to write up a proof completely and totally from scratch. We're building into that set of skills, and with our first unit, we'd just like you to be able to complete the missing sections. So basically, it's a fill-in-the-blank style proof. What's the missing topic? What's the missing piece? And so we'll start off here. A gardener has 26 feet of fencing per garden. To find the width of a rectangular garden, the gardener uses the formula perimeter equals 2 times length plus 2 times W, where P is the perimeter, L is the length, W is the width. The gardener wants to find the garden. The gardener wants to fence a garden that's 8 feet long. How wide is the garden? Solve for Q, solve the equation for W, and justify each step. So anyhow, I rushed through that all because, ta-da, we have the work already. We already have all the algebra. And the only things we need to do are find the missing sections, like here with number 1, and there with number 2. What's missing? Now, admittedly, this is kind of a little bit of a scary skill because you're not actually writing the proof yourself. You don't actually need to, at least for this one, we don't need to understand the algebra as long as we can understand the step that we're searching for. It's a dangerous skill, and of course we do expect that with time you'll get above this level. But what we're noting is the given tells us here what will allow you to conclude that this is true. To go from line 1 over to line 2, what did you do?
L equals 8.
We put in L is 8, we put in P for 26, and those are substitutions. We don't need to build the proof, we just need to be able to analyze it right now. Continuing down to the second part, when we reach here, we are at the line, we're at the equation, 10 is equal to 2W. What's different going down to the next line? What did you do? Yeah, we divided. So what allows you to divide both the left and right hand side?
Division property of equal.
Yes, Stephen, we've got the division property of equality. And of course we know that we have the additive property of equality, subtraction, multiplication. We've got these properties that say, go ahead. And we'll continue the same piece. For question number 9, write down a justification for each step.
Hello.
Now, to continue the problem, to continue or rather start this question number 9, we are starting right here with number 1. Where does this equation come from? The measure of angle JKL plus the measure of angle JKM. The measure of angle JKL equals the measure of angle JKM plus the measure of angle MKL. Except, you know, normally, step number 1 for most problems will be the given. Not 100% though. Our given was the picture. Our given was that the measure of angle JKL is 100 degrees. We were not given the equation right off the bat. That came from somewhere else. In particular, this is a problem where you would have to recognize angle JKL, J to K to L, that's the entire thing. JKM, J to K to M, that's this piece. MKL. MKL was the second part. You are expected to recognize that this equation came from taking piece plus piece equals the whole. And we know that when you take the piece plus the piece to equal the whole, that was the angle addition postulate, going back to our previous unit. Remember with our previous unit that we also had the segment addition postulate, where we could take piece plus piece to equal whole for segments? Obviously, it would make sense that at least one of those things will pop up during our exams, simply because we don't ever forget the stuff we did.
Wait, what's that called?
And just to elaborate, one person was asking about the spelling. POST with the period was an abbreviation for postulate. Right, let's continue going down. They use substitution and start simplifying. They subtract. To go from this line down to here, what has changed? What did we do? To simplify it? Okay. And when we simplified it, what did we have to do? We used division again to get that level of simplification, so we are once again using the division property of equality in the video. The big difference on why we did not use the word simplify, up here, when they combined the 6x and 2x, those were already on the same side of the equal sign, so we were simplifying one side. Down here with our blue, we were actually dividing on both sides. That's why it was an equality property. For question number 10, which property is getting used? You ought to recall the three different properties we were searching for were the reflexive, symmetric, and transitive. Which one is this? Now, of course, we need to remember what each one of these properties is. The reflexive property is used to say something like AB is equal to AB. And this would be the reflexive property of equality because we're using an equal symbol. When we use segments, we would have the reflexive property of congruency. The symmetric property was used for pieces like AB is congruent to BA. And the transitive property was used for pieces like AB is equal to CD and CD is equal to EF, so we can get down and say AB is congruent to EF. When we're using congruency, we've got congruent. Symmetric, want to elaborate, was used if you know AB is congruent to BA, we'd be able to say BA is congruent to AB. So anyhow, which one of these three is it? Just looking at the structure, we should recognize that this is the transitive property. And since we are using a congruent symbol, it's the transitive property of congruence. Continuing further, fill in the blanks to complete the two-column proof. We'll start by noticing the given. Angle 1 is supplementary with angle 2, and we're given the measure of angle 1 equals 135 degrees. And we're trying to prove angle 2 has measure of 45 degrees. So running through them. First piece here with number 1. What statement do we know is true since it was given? Of course, we'll go right back up to the top and see we've already used the fact that they're supplementary. So we need to know the measure of angle 1 equals 135 degrees. Continuing further here to statement 2, we need to ask ourselves then, where did this line come from? We know that the measure of angle 1 plus the measure of angle 2 equals 180 degrees, but where did it come from? Please keep in mind that we can only use the stuff that's already been written down, and so the only two things that we have at our disposal were supplementary angles, and that angle 1 is 135 degrees. You should recognize then that supplementary, that's exactly what this stuff is. The definition of supplementary tells us two angles add up to equal 180 degrees. Continuing down further, to go from line 4 down to line 5, we recognize that what's changed? Well, to solve this equation, we would have had to subtract 135 from both sides, and 180 subtract 135 is where the 45 degrees came from. So recognizing that, we can tell that we've used the subtraction property of equality since we subtracted from both sides of the equation. Number 12, use the given plan to write up a 2-column proof. First of all, given, given, given. We have 3 pieces of given, and we're trying to prove that the measure of angle 1 would equal the measure of angle 4. Please remember that, though, that the plan doesn't tell you every tiny little detail. It's the big picture idea. Nevertheless, we can use the plan to write up the proof. So running through, measure of angle 1 plus measure of angle 2 equals 90, that's given. For line number 2, what other statement was given? Well, we used that one already. Just keep it in concert, measure of angle 3 plus the measure of angle 4 equals 90. All right, we've got that one built from the given. We can see then that line number 2 and line number 1 were substituted to create line 3. Using, or rather introducing the given from line 4 will allow us to progress. How do we go from line 3 to line 5? Well, what we need to observe is what's different from them. The only difference is that measure of angle 3 has been replaced with measure of angle 2, and in line 4 we saw that those were the same, so this is a piece where we applied substitution. We replaced angle 3 with angle 2 because they were the same, or their measures are the same. Then lastly, to go from line 5 to line 6, what's different? The angle 2 measurements are gone, and so when you subtract off the measure of angle 2 from both sides, you can do that by applying the subtraction property of equality. Problem 13, use the 2-column proof to write a flowchart proof. So what it's asking us to do is to convert a 2-column proof into a flowchart proof. That should be fairly straightforward because we know with a flowchart proof, each line, the box, is the statement. And the reason is tied right below it. Therefore, it's pretty easy to recognize what needs to go into the flowchart proof because we can identify the reason right here, and we know that the box is going to be the statement that's tied with it. We'll just come back up and we can see right here, we are using the definition of a linear pair, and so the box it has to be tied to is right here. This is what goes into it. Angle 1 is supplementary with angle 2. Angle 3 is supplementary with angle 4. And I don't like how this it looks blended together there. Angle 1. And of course, We'll continue and do the exact same thing. Next, we need to identify the reason here. Well, the reason and the line are tied together. Given that right here we have angle 2 is congruent to angle 3, we just need to find that, and it's tied perfectly together. We could change the format then and use the congruent supplements theorem and our last problem will be similar. Use the two-column proof to write out a paragraph proof. Well, here we are again. The two-column proof and the paragraph proof, they're tied together. Each line in the each line in the two-column proof is a sentence in the paragraph. Well, coming down to the bottom, since number 1, angle 1 and angle 2 are right angles, that is a line in the proof. Well, here are angle 1 and angle 2 are right angles. That has to be tied in with its reason. So we'd be able to say, since congruent supplements form right angles, angle 1 and angle 2 are right angles. And we could continue further, coming down here to number 2. We'll have to read the sentences. By the definition of congruent angles, 2. So where do we use the definition of congruent angles? Right there. It's tied with its statement, so we'll simply bring these in and say the measure of angle 2 equals the measure of angle 3, and we're done. A simple translation, recognizing that every sentence in the paragraph is a line in the two-column proof. Every sentence in a paragraph would be a box and just a reason in the flowchart proof.